This is Daryl with Cisco Hands-On Training. Today we're going to talk about VLANs and spanning tree. It's the 28th of January 2009. The website is www.ciscohandsontraining.com. I'm going to put today's diagram on the website, and to subscribe in iTunes, it's easy. Just search on Cisco Podcast and you'll see us near the top. One correction from the last episode. During last week we were talking about ARP, and we were talking about Ethernet broadcasts, and Ethernet broadcasts have a target MAC address of all Fs, FF, 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 FF. What I want to correct is, let's look at the TCP dump of an ARP request. Here's a TCP dump, and you can see I'm using the double verbose option, and the -N option means that the addresses in there are printed out. And so you can see this box is generating an ARP request, and it sends it from my source MAC address to the broadcast MAC address. The Ethernet type is 0806, which is saying that it is an ARP packet inside there. And the ARP request is whoever it wants to identify who has IP address 10.0.1.34, please tell me, and I'm at 10.0.1.197. Now let's look at the ARP format. In the ARP format, we have, and I got this off Wikipedia, in the ARP format we have the sender hardware address, which is 48 bits, and then we have the sender IP address, the sender protocol address, which is 16 bits. I'm sorry, 32 bits. And then we have the target hardware address, which is 48 bits, and then the target protocol address, which is 32 bits. Let's find those fields in our TCP dump up here. And in this TCP dump, I have the full hex dump. So the way to start is the sender hardware address. Our hardware address is 001F5BD08F8A, and here it is. Here's the sender hardware address in the ARP request. And then immediately after the sender hardware address, we have the sender protocol address, which is 10.0.1.197. And here it is. Here's 10, 0A, A is 10 in hex, 10.0.1. And then C5, presumably 197 in hex. So you can see in the ARP request, here is the originating MAC address, here is the originating IP address, and then we have the target hardware address, and the target hardware address is all zeros. And the reason is because this is a ARP request. We're trying to find out the target hardware address. If we continued the packet trace of the ARP, we would see an ARP reply, and in the ARP reply, these 48 bits would be populated with the MAC address of the target. And then finally we have the target protocol address, which is 10.0.1.34. And here it is. 10, 0A is 10 in hex. Dot 0, dot 1, dot, and then 22 is 34 in hex. Okay, so that's what an ARP request looks like. And I guess the key message from that is in the ARP request, the ARP request and the ARP reply look very similar. It's just in the ARP request, the target hardware address is left blank, and then in the ARP reply, they fill that in. So that's a little bit of follow-up on ARP. Let's get on to VLANs and spanning tree. A VLAN is a virtual LAN. It's like a virtual switch. Last week we learned how switches work. A switch attempts to intelligently forward frames out of port. It tries to figure out which port a particular MAC address is out and only forward the frames out that port. That improves performance because you have less collisions on the net. But since you have a switch, one of the technological improvements is VLANs, where you can have like 10 VLANs or 20 VLANs on a switch. Each one's like a virtual switch. So let's look at this diagram. I have one switch for the lab that I'm doing today, and then one router. But I'm configured 3 VLANs on my virtual switch. So VLAN 2, VLAN 3, and VLAN 4 are all like 3 virtual switches. And then what I'll do is I'll build a virtual triangle by connecting Fast Ethernet 0/21 on VLAN 2 to Fast Ethernet 0/30 on VLAN 3. And that way it's just like having a connection between 2 different switches. Ethernet switches forward Ethernet broadcasts destined to MAC address FFFF, and unknown unicasts, unicast to a MAC address which is not in the MAC address table on the switch. It forwards these out all ports to emulate the old hub behavior. That's called flooding. But if you have a loop in your network like this, and this router were to initiate a Ethernet broadcast, then if the virtual switch for VLAN 2 flooded that broadcast out both ports, and then each of these switches flooded it, then you would have a loop in your network. The frames would just circle in your network again and again and again, and you'd suffer a bandwidth outage. So what we need to do is we need a protocol which will allow us to keep redundancy in our network by having these loops, but it will temporarily block some of the ports in the loop. And that is called spanning tree protocol. The purpose of spanning tree protocol is to eliminate loops in your network, so that way you can build loops and it will temporarily disable them, so that way you have redundancy, but you don't suffer a bandwidth outage because frames are circulating in your network. The spanning tree algorithm is to pick a root bridge, and then that's the center of your tree, of your topology. And then each other bridge will determine the least cost path to the root bridge, and then all other root paths will be disabled. So when you turn the network on, each bridge will send what are called BPDUs to the other bridges, and it'll say, hey, I think I'm the root. I think I'd be a good root bridge. And the BPDUs contains this information, and again I've specified my source here, networkninja.co.za. And in here, some of the key fields, we have the root ID, which is we have the bridge ID, which is the bridge that's sending the BPDU, and the root ID, which is the information on the current root. And that has 8 bytes. The first 2 bytes are the priority, which is by default 32.768, and then the last 6 bytes are the bridge MAC address. So the lowest bridge ID will win, and losers, which other bridges which are, I'm using the term bridge here. A bridge and a switch are the same. A bridge is just an older term. When they started, originally bridges were like 2 ports, 3 ports, 4 ports. They'd intelligently forward the frames just like I described for switches. And then over time, switches came out that had 24 ports, 48 ports, 300 ports. They called them switches, but a bridge and a switch are in effect the same. They're all layer 2 devices. They're making intelligent forwarding decisions based on the destination MAC address. And they generally run the spanning tree protocol to try to eliminate loops in the network, so you don't suffer a bandwidth outage. Okay, so each bridge or each switch has its bridge ID. They each try to become the root of the spanning tree, but they all send BPDUs to each other with their bridge priority. And that bridge priority has the default 32.768 appended by the MAC address as a tiebreaker. The lowest priority wins. So in effect, if you leave a bunch of switches at the default configuration, then whichever switch has the lowest MAC address will become the root bridge and the center of your topology. The losers will not originate BPDUs anymore. Instead, they will receive the BPDUs from the root bridge and forward them on out the other ports. Each segment picks a designated port that's closest to the root bridge, and that's enabled. All other ports become blocked, and that eliminates loops. Each segment has a designated, each segment picks a designated port closest to the root bridge. So Wikipedia has a good example, so let's go through that. Here is a switch topology. We have 1, 2, 3, 4, 5, 6, 7 switches in the network, and the number indicates the bridge priority, and again, lowest wins. So at first, all of these switches, if they were all turned on simultaneously, they would all start sending out BPDUs saying, I'm the root bridge. The first thing that will happen is all these BPDUs get to all the other switches, and eventually the switches will agree that whichever one of these switches has the lowest priority, the lowest lowest bridge identifier, which is a priority followed by the lowest MAC address, will become the root bridge. In this case, switch 3 will become the root bridge. Okay, so here we have the root bridge, which is 3, and then the next thing that the switches will do is the port that is closest to the root bridge will be called a root port. So here on switch 24 it has 3 ports, but assuming that bandwidth is equal on all of these links, the port up here on the top will become the root port. Likewise for switch 92, the port here on the top will become the root port. So here we have the root ports identified for each of the switches. So you can see that in the root bridge, every port is forwarding. In these other switches, the root ports are forwarding, and we're building a tree. The next thing that we do is on each segment, it needs a designated port. A designated port is the port on that segment which is closest to the root bridge. Now obviously up here, the designated port, these ports connected directly to the root bridge, will be the designated ports. On this segment, for example, it has 2 possibilities for designated port. It could be this port over here or this port over here. And again, our tiebreaker is the lowest bridge ID. The lowest bridge ID, since each of these ports is equidistant from the root bridge, the port that's connected to the switch with the lower bridge ID will become the designated port. So here we are with all of our designated ports identified. You can see our designated port here, our designated port here, and so we have 1, 2, 3, 4, 5, 6 designated ports here for 1, 2, 3, 4, 5, 6 segments. And then all other ports will become blocked. So in this segment D, because this port over here is designated, the other port is blocked. In segment F, because this port is designated, this port is blocked. Blocked ports will not forward frames. So what we've done here is, in effect, we've built a tree. The root bridge is the center of the tree, and then all of the segments will forward only towards the center of the tree. But we still have our redundancy. If this port went down on this bottom of this switch 24, then the old designated port would no longer be effective, and BPDUs from this switch won't make it to switch 4. Switch 4 will eventually realize that and then pick a new root port headed towards switch 5. So we'll have a new designated port close to switch 5. 4 will have a new root port, and then segment C will have a new designated port. So we eventually will reroute around the failed port. So spanning tree protocol is a way to avoid loops, because in this topology there's no loop. There's no way to get from 4 back to 4 by any path. There's no way to get from 92 back to 92 without going through a blocked port, and of course blocked ports are blocked. So that's the Wikipedia example of the spanning tree protocol. Let's go ahead and log into our switches and configure according to this diagram. So here I am on a switch, and what I'm going to do is I'm going to configure ports. I'm going to use VLANs 2, 3, and 4, and I'm avoiding using VLAN 1 just out of habit, because it's generally good to avoid using VLAN 1 because it's special in some ways for security reasons. And so I'm going to configure all ports from 20 to 29 in VLAN 2. I'm going to configure all ports in 30 to 39 in VLAN 3, and I'm going to configure all ports in 40 to 49, 40 to 48. So it's a 48 port switch in VLAN 4. So VLAN 2, and then this enables the VLAN, and I can give it a name Bob. VLAN 3, name IT, VLAN 4, name accounting. So you can issue your VLANs names. And now I show the VLAN, and when I show the VLAN, you can see VLAN 2 is named Bob, VLAN 3 is named IT, VLAN 4 is named accounting, but more importantly, the VLANs actually exist now. So let's configure our ports on the VLANs. So conft. Now here's this is a layer 2 switch, so I can't configure IP addresses on these ports. Let me configure the ports into different VLANs. And on a switch, you have a lot of ports, so you want to configure the ports efficiently. So let's use something new, the interface range command. Interface range fast, because it's fast Ethernet, 0/20 to 29, switch port mode access. Switch port access VLAN 2. So switch port mode access is setting the port to be an access port and not try to become a trunk. And I'm setting all 10 of these ports on VLAN 2. And then int range fast 0/30 to 39. And let me switch port mode access, switch port access VLAN 3, int range fast 0/40 to 48, which is the max of my switch. Switch port mode access, and then switch port access VLAN 4. Now here's an interesting log message, native VLAN mismatch. I have cables connecting fast 0/21 with fast 0/30. They're Ethernet crossover cables, and so VLAN 2 is connected to VLAN 3, and the switch has detected that thanks to the CDP protocol, and it's decided to give me a warning because it thinks that I didn't intend to do that. And so the error message is CDP native VLAN mismatch discovered between fast Ethernet 0/30, which is on VLAN 3, with fast Ethernet 0/21, which is on VLAN 2. Okay, fine, I got the warning. It'll repeat every now and then. It's sort of annoying, but it's okay. So show CDP neighbor fast 0/21, and you can see on fast 0/21, my neighbor is my own switch on fast 0/30. I do show VLAN, and it's the table's a little messed up here, but you can see VLAN 2, which is named Bob, has fast Ethernet 0/20, fast Ethernet 0/21, 0/22, and so on. VLAN 3, which is named IT, is fast Ethernet 0/30, fast Ethernet 0/31. let's look at spanning tree. Show run type include spanning tree. My spanning tree mode is per VLAN spanning tree. So this is the traditional spanning tree. So it's it's an old protocol, several years old. There are recent enhancements to it, like rapid spanning tree and MST, which is a multiple spanning tree, where you can have one spanning tree instance per or to serve multiple VLANs. But today we're covering the old original spanning tree. We'll cover rapid spanning tree in a future class. Per VLAN spanning tree means it's running a spanning tree instance per VLAN. So it's accurately emulating the fact that these are three separate virtual switches. The box will run spanning tree on VLAN 2, run a spanning tree on VLAN 3, and run a spanning tree on VLAN 4. And they'll actually send BPDUs to each other. Let's do show spanning tree. So it shows me the spanning tree instance for each spanning tree instance, of which I have 3. And you can see for spanning tree VLAN 0002, my spanning tree priority is 32770, which I guess is the default on this switch because I have not configured anything. And it tells me that the root bridge address is 0018BA10E800, and it says that this bridge is the root. The hello time, which is how often the switches send BPDUs to each other, is 2 seconds, and the max age is 20 seconds. Now, by max age being 20 seconds, remember when a port went down, eventually this switch detected that the port went down. It will detect that the port went down after it has not received a BPDU in the max age time. So it's expecting to receive BPDUs every 2 seconds. If it does not receive a BPDU for 20 seconds, then it will decide that it had a failure, and it'll need to designate a new root port. So when in spanning tree, traditional spanning tree convergence is a bit slow, because in this case it does not even detect the outage for 20 seconds. You lose a link, and only 20 seconds later does your switch begin to try to reroute around it. And that's why they invented later rapid spanning tree. Okay. And then my ports, since I am the root, all of my ports will be forwarding. And there's a cost associated with each of the ports, which is based on the spanning tree protocol. The fast Ethernet 0/20 has a cost of 100, and fast Ethernet 0/21 and 22 have costs of 19. Well, why is that? Well, show int fast 0/20. It's a fast Ethernet port. It's up. But the bandwidth is only 10 megabits. And the reason is because it's connected to one of the old 2500 routers with a 10 megabit Ethernet connection. So even though it's capable of running fast Ethernet, it's currently, it cannot negotiate at 10 megabit or 100 megabit, and it has negotiated 10 megabit because it's connected to an old router. So the cost of a 10 megabit port is considered 100 in spanning tree, whereas the other ports, show int fast 0/21, this connects to another switch. When it connects, it's connecting at 100 megabits. So show spanning tree VLAN 2. So the root port cost takes into account the bandwidth, and a fast Ethernet port has a cost of 19, and a old 10 megabit Ethernet port has a cost of 100. And all ports are forwarding on the root bridge. Let's look at the other VLAN. Show spanning tree VLAN 3. And it says that, notice that spanning tree 3, it prints out the root ID information, and it says the root ID is this MAC address, which also happens to be my MAC address because it's because this is one switch with multiple VLANs. But the root port is actually out fast Ethernet 0/30, and it has a cost of 19 to get there. So let's look at our map. Here's VLAN 3. And VLAN 2 is our root bridge. And out fast Ethernet 0/30 is my root port, which is the port that is closest to the root bridge, which makes sense because fast Ethernet 0/30 connects to the root bridge. And the cost to get to the root is 19, which makes sense because the cost is one fast Ethernet link, and a fast Ethernet link has a cost of 19 in spanning tree. Okay, so again, VLAN's 3. The root ID, the root bridge, we know the root bridge MAC address, which is cool. We know the root bridge is a cost of 19 away. We know that to get to the root bridge, we go at fast Ethernet 0/30. And so fast Ethernet 0/30 is the root port, and it is forwarding. And then fast Ethernet 0/31 is a designated port for this segment, and it is also forwarding. So at this point, I'm forwarding on all the ports on VLAN 2. I'm forwarding on all the ports on VLAN 3. So I would expect to be blocking on one of the ports on VLAN 4. In fact, if I look at it, I would expect to be I would expect that fast Ethernet 0/41 would be the root port, and fast Ethernet 0/40 would be the blocking port, because fast Ethernet 0/31 is the designated port for this segment, and each segment can only have one designated port. Show spanning tree VLAN 4. And then here on spanning tree VLAN 4, again, it tells us what the MAC address is of the root bridge, and it tells us the cost to get to the root bridge. It tells us that the root bridge is out fast Ethernet 0/41, and it tells us that the root port out fast Ethernet 0/41 is forwarding, and we have another port, fast Ethernet 0/40, which is an alternate port, which means that it's a Cisco optimization to try to fail over more quickly in case the root port goes down, and it is currently state blocking. Okay, so let's go ahead and for kicks, well, so fast Ethernet 0/40 is blocking. So in effect, our tree, we've built a spanning tree. VLAN 2 is the root, and we have a leg over to VLAN 4, and we have a leg over to VLAN 3, and the connection between VLAN 4 and VLAN 3 is blocked at fast Ethernet 0/40. So we have a tree with no loops in our net, and that's cool. For kicks, that's exactly what spanning tree is supposed to do. For kicks, let's conft int fast 0/41 shut. Show spanning tree VLAN 4. Show spanning tree VLAN 4. And I'm getting a bit of data here. And you can see that spanning fast Ethernet 0/40, which was the alternate port, is now learning, and now it is forwarding, and it's the root port. So let's go back and look at a little bit of what happened there. So the spanning tree for 0/40, 0/40 was blocked, and it was a alternate port. But once we shut down 0/41, this switch immediately detected it because, frankly, it was a shutdown. I shut down the port. Or if I lost link on the port, then it would have detected it immediately too. If you have a remote connection where you still have link on your side, but the other side isn't sending you the BPDUs anymore, that's when it might take you longer. That's when you might have to wait the 20 seconds to stop getting BPDUs to detect it. But in this case, we detected it immediately. So great. We detected a failure in 0/41 immediately. Let's start. We want to start forwarding on Fast Ethernet 0/40, but let's be a little bit cautious about it, because the last thing we want to do is cause a loop, which would cause a bandwidth failure in the net. So we make Fast Ethernet 0/40 a root port, and we listen. Spanning tree goes through these phases where it listens, and it does that for a forward delay of 15 seconds. And when it's listening, it's just listening for BPDUs and letting things stabilize. And then it goes into a learning phase for another forward delay, which is by default 15 seconds. And during that learning time, it will learn MAC addresses and fill up its MAC address table, but it will not forward yet. And the purpose of this is it wants to avoid flooding traffic, so it wants to fill up its MAC address table as much as possible so it can make intelligent forwarding decisions as opposed to flooding traffic all ports. And then after another 15 seconds, then it will move into the forwarding category. Okay, let me do the no shut on the other port. Int fast 0/. Let me try a logging command. Logging events. Int range fast 0/1-48. Logging event spanning tree. Yeah. Conf t int fast 0/41 no shut. Show spanning tree VLAN 4. Show spanning tree VLAN 4. Wait a few more seconds. So you can see here that port 0/40, it's back to an alternate port, it's blocking, but the new root port is just listening. Again, we're being cautious. And now the root port is learning. So it's not actually forwarding traffic, but it's learning MAC addresses. And it's being cautious. And it's doing that for another 15 seconds. And now it's finally forwarding. So when we re-enabled our correct uplink port, we took a 30-second hit because we had to wait while the switch was being cautious and going through listening and learning states before it really decided that it could safely forward out that port without causing a loop in the traffic. So spanning tree is a good protocol because it avoids loops in your network, and it avoids loops in your network and allows you to keep redundancy, but it still takes a long time to fail over. And it can typically take 30 to 50 seconds for spanning tree it takes 30 seconds for spanning tree to fail over, and in some cases it can take an additional 20 seconds to detect that a failure has occurred. So you're talking like 50 seconds. Well, spanning tree is being pretty cautious here. Let's learn why spanning tree is being cautious. We have as an experiment, we have a loop in our network and spanning tree is blocking it. Let's turn off spanning tree and see what happens. No spanning tree, VLAN 2 to 4. Okay, so no spanning tree. Spanning tree does not exist. All of my ports are going to start forwarding, so I've got a loop. Show int fast 0/41. And my input rate is still slow. And that's because there's no traffic on the net to start flooding. Let's create some traffic. Conf t int VLAN 2. Let's configure my management IP on this switch. I'm allowed to have one. IP address 10.1.1.2, 255.255.255.0. show int so ping 10.1.1.2, I'll ping myself. Ping 10.1.1.1, that's the router that's out there. Or at least it was supposed to be the router. I don't know that I configured it. So right now I'm ARPing for 10.1.1.1. And the ARP is an Ethernet broadcast. And the Ethernet broadcast will be flooded. And let's see if anything bad is happening. Show int fast 0/22. Look at that. Right now my input rate on the interface is 1800 packets per second. So that ARP request that I sent out is being flooded around the network, and it's just circling and circling and circling. Let's look again. Yep, I'm getting 3,000 pack. I did one ping, and I have a loop in the network, and I'm getting 3,000 packets per second, and that's 1.6 megabits going around in a circle. Show proc CPU. Take a look at this. Because so many packets are coming in, my CPU on my switch is at 86%. And let's look what's doing it. ARP input is 19%. And interrupts are 55%. Well, we'll talk about what these different things means later. But basically, I have a loop in my network because I turned off spanning tree, and packets are just circling and circling and circling, and any box attached to that net is going to go to 100% CPU, including the routers. And that means they're not going to be able to process routing protocols, and you're going to suffer a major outage. This is called a spanning tree loop outage. But really, it should be called a lack of spanning tree outage. It's not that spanning tree caused the outage, it's that spanning tree failed to prevent the outage. The job of spanning tree was to prevent the loop, but we have a loop in our network now. You are particularly vulnerable to spanning tree loops in buildings with lots of Ethernet switches that you don't have control over. So in desktop networks where you have a campus building, you have 500 people working there, they're all plugging hubs in their cubes. Sometimes I've seen people plug hubs into each other, and they can change your network topology in a way that you don't expect, and as a result, spanning tree may fail to prevent the loop from occurring. When that happens, the way to fight it is to identify that you probably have a spanning tree loop, and okay, so your routers are at 100%, your switches are at 100%, and ARP input is very high. That's a clear indication of some sort of spanning tree loop. You do a show int pipe include load to try to see what interfaces the loop is on. And here, show int pipe include load, looking down, it's all 1, 1, 1, 1, 1, 1, 1. And then right here on this interface, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The 22nd interface is the first one where I have a transmit load of 81. And then the 23rd interface is where I have a receive load of 15. The 23rd and the 24th interface. So let's do a show, that's sort of painful, but show IP int brief. So the 23rd interface is the first one where we have a high receive load, and we have two interfaces that are VLANs, and then we get in our numbered fast Ethernet. So if the 23rd interface counting is the one where we're receiving lots of traffic, that means fast Ethernet 0/21 is maybe where we have a problem. Well, let's confirm that. Show int fast 0/21. And you can see that our input rate is about 8 megabits per second. We're now getting 15,000 packets per second here. And the way to fight the loop is to eliminate the loop. So by shutting down fast Ethernet 0/21, we will eliminate the loop. Our network will still be up because we still have redundancy, but our CPUs will drop on our routers and switches. So conft, so let's look at this. Show proc CPU, see our 5-second, I got garbled a bit there. Show proc CPU. So we have 88% CPU right now. Conft int fast 0/21 shut. Show proc CPU. And you can see I've eliminated the loop. My 5-second CPU is already dropping dramatically. That's the 5-second average. Now it's more than 5 seconds later. 10 seconds later, I eliminated the loop, and the CPU is down to nothing. So that is what a spanning tree loop looks like. And it's really not a spanning tree loop, it's a lack of spanning tree loop. But basically we deliberately disabled spanning tree to cause an outage. We have a loop in our network, and all it took was one ARP request to start circling the net, and pretty soon we had 15,000 packets per second going back and forth, and it caused all routers and all switches attached to the net to go to 100% CPU. The show proc CPU shows high CPU, particularly in the ARP input category. Here you can see the ARP input, and the 1 minute and 5 minute CPU stats are high. And the way to fight a spanning tree loop is to eliminate, you either find out the cause of the loop, or the best thing to do is to just eliminate the loop. And simply shutting down one of the ports in the loop is often effective. Okay, so that is spanning tree today. To review real quick, switches can have virtual LANs, so you can make virtual switches, and you can use those for different things, like you could have different VLANs for different subnets for different departments. But when you connect these switches together, you want redundancy, so if you lose a link, you fail over. But Ethernet floods certain frames, so to avoid flooding in a loop, you need a protocol to automatically eliminate loops for you. And the spanning tree protocol is the traditional protocol to do that with. Spanning tree converges slowly. If it suffers a failure, it might take 20 seconds to detect the failure, which is the const spanning tree VLAN 2 to 4. Show. Yes, so the max age is 20 seconds. So if the hello time is 2 seconds. So the switches, your switches will elect a root bridge. The root bridge will generate BPDUs every 2 seconds. Those BPDUs will be forwarded on by other switches. If a switch fails to receive a BPDU for 20 seconds, then it will determine that links back to the root bridge is broken, and it will attempt to look for an alternate path. Once it looks for an alternate path, once it finds an alternate path, it will be very cautious about beginning to forward on the alternate path. It will wait for a listening time and a learning time, which is another 30 seconds before finally forwarding on the alternate path. And all this caution is to try to avoid a spanning tree loop. A spanning tree loop is where somehow the spanning tree protocol has failed to prevent the loop. The frames are being flooded in a circle around your net, causing all of your devices in the net to go to 100% CPU. The way to fight it is to recognize that it is a spanning tree loop. You recognize it by the high CPU, by the high traffic utilization on certain interfaces, particularly the ones between your switches, and you stop it by eliminating the loop, by shutting down one of your interfaces to eliminate the loop. Okay, that's it for today.